Welcome to the deep dive. Today we're digging into a new research paper, Test Time Training Done Right. We're using just this paper as our source, focusing on their new approach for AI modeling of long data sequences. Our goal here is really to unpack the technical ideas behind large chunk test time training, or LaCT. We'll look at how it works, the architecture, and what the experiments show.
Okay, so let's start with the background. Test time training, TTT, it's this idea where you have part of your model, these fast weights that you actually update during inference time as new data comes in. You can think of them as a kind of adaptive memory learning context on the fly. It's been seen as, a potentially efficient way to handle sequences, maybe better than standard attention, which gets costly with length.
Right. That quadratic cost is a killer for really long sequences. So TTT sounds promising, but the paper argues existing methods haven't quite cracked it for very long sequences. What's the technical problem they hit?
Yeah, the big hurdle seems to be computational efficiency, just getting the hardware, like modern GPUs, to work efficiently. Existing TTT methods, they often get really low hardware utilization. The paper mentions numbers like below 5% FLOPs utilization.
Wow, less than 5%. So the expensive hardware is mostly just waiting.
Wow.
Why does that happen, technically?
It mostly boils down to how those fast weights get updated. Traditionally, it's done with really small online mini batches, maybe 16 tokens or 64 tokens. And while that might work for some learning setups, for these big parallel processors, these tiny updates just don't give them enough work to do at once. It creates poor parallelism, low compute intensity. It becomes a real bottleneck if you want larger nonlinear fast weights too. And there's another angle. That small batch approach implies this very fine-grained, almost token-by-token causal dependency. That doesn't map well to data like images or videos, which have, 2D or 3D structure, or even just sets of things. Implementing that efficiently, especially with complex fast weights, is just technically tough.
Okay, so the old way was like processing tiny steps, which GPUs aren't really built for. And this paper's LCT approach goes the opposite direction with really big chunks. How does that change things technically?
It's a fundamental shift in scale. We're talking chunks from maybe 2,000 tokens all the way up to 1,000,000 tokens in some of their experiments. Much, much larger.
1,000,000 tokens in one go.
Yeah, for certain tasks. And this large chunk approach brings some major technical benefits. First, hardware utilization. They report huge jumps up to 70% on an NVIDIA A100. That's going from, less than 5% to potentially 70%. The hardware is actually doing serious work now.
That's a massive difference in efficiency.
It is. And that efficiency unlocks other things. It makes it feasible to scale up the size of those nonlinear fast weights. They show they can scale this state up to like 40% of the model's total parameter size. That suggests a much bigger capacity to store context compared to older TTT methods, where that was limited by the update costs.
So better efficiency allows for bigger, potentially more powerful internal memory states.
Right. And another technical plus is simplicity. They say the core LaCT logic is just dozens of lines of standard PyTorch code, no need for custom CDA kernels or anything super specialized. That's actually a big deal because it makes it easier to experiment, to plug in more sophisticated optimizers for those fast weights, like the Muon optimizer they use.
Easier to build and tweak then.
Definitely. And finally, the large chunk idea fits naturally with n-dimensional data. You can make a chunk correspond to a whole image or several video frames. It aligns the processing with the data's inherent structure.
Okay, processing big, meaningful blocks that suits the hardware and the data structure. Let's get into the architecture itself. What are the main components of a LCT block?
Sure. If you look at their diagrams, like Figure 2, a typical LCT block has three key parts. There's a window attention layer, the large chunk TTT layer itself, and then a standard feed-forward layer. And usually residual connections around them, which is pretty standard stuff.
Let's focus on that large chunk TTT layer. How does it technically handle the updates compared to the old way?
The core technical difference is the update operation, shown in their equation 4. Instead of updating per token, LCT calculates one gradient update based on all the keys and values within that entire large chunk. It sort of averages out or amortizes the update cost across thousands of tokens. The network doing this update, the fast-weight network, is described as a Sui-Jiu MLP without biases, a type of feed-forward network common in large models. The loss guiding that update is pretty simple, just a dot product based on representations from the chunk.
And how are those updated fast weights used? The apply step.
Right, the apply operation, equation 2. Here, all the query vectors within that same chunk use the same single updated fast weight state that was just computed for the chunk. This separation of update and apply for the whole chunk gives you some interesting technical flexibility. You can change the order in which you do update and apply across chunks. As they show in Figure 3, different orders create different data dependency patterns, like different kinds of masks in attention. You could do a full mask or a blockwise causal mask where each chunk depends on the previous one. For language models, they use a shifted order. Apply the old state first, then update based on the current chunk. That keeps it causal, prevents seeing the future within the chunk.
So apply then update maintains causality for sequential tasks like text.
Exactly. And they also mention a strided approach, where you might only update the fast weights every few chunks, saving computation.
Okay, clever ways to manage dependencies with the chunk ordering. What about the updates themselves? You mentioned nonlinear updates and optimizers like Muon.
Yeah, updating these fast weights online needs care to avoid instability. They use nonlinear functions, specifically swglu, for the fast weights. And they look at update rules beyond basic gradient descent. There's a vanilla update using gradient descent with L2 normalization, but they also highlight the Muon update rule. Muon tries to stabilize things by normalizing the spectral norm of the gradient, basically controlling the size of the gradient update in a specific way. They also consistently use L2 normalization on the fast weights themselves after each update.
So Muon helps keep the online learning stable. Now, you mentioned the TTT layer treats the chunk like a set for its update. How does the window attention layer fit in? Why is it needed?
That's a crucial point. The large chunk TTT layer, by processing the whole chunk for the update, doesn't inherently capture the fine-grained order inside the chunk. Like the spatial layout of pixels in an image chunk or the word order in a text chunk, that's the job of the window attention layer. It operates locally within a window or chunk to explicitly model those local dependencies and internal structures. It handles the fine-grained stuff.
So it's kind of division of labor.
Exactly. It's a hybrid architecture. Window attention handles local structure using quadratic compute, but only over a small window. The TTT layer handles the longer-range, non-local context across chunks, using linear compute relative to the sequence length thanks to its fixed-size state. It lets the TTT state focus on the global context.
That technical split makes sense. Local attention, global TTT state.
Mm-hmm.
The paper also mentions context parallelism. How does auto-regressive help distribute the work?
Right. Context parallelism is about splitting a single long sequence across multiple devices. Standard layers like feed-forward or window attention are usually easy to parallelize this way because they're local, but traditional TTT with its sequential small updates is tricky. LaCT's large chunks make it easier. You can split or shard the tokens within one large chunk across your devices. Since the final chunk gradient is just the sum of gradients from each shard, equation 11, you can compute these parts in parallel and then combine them. It's similar to data parallelism, but applied within the processing of a single long sequence by splitting the chunks. They mention it worked well with low overhead.
Okay, so the architecture seems quite flexible. How did they technically configure LLCT for the different data types they tested? Image sets, language, video.
They tailored the setup quite specifically for each task. For novel view synthesis predicting new views from a set of input images, the chunk was the entire sequence of images, sometimes up to 1 million tokens, maybe 128 images. The TTT layer used a strided causal mask setup, updating on all the input views and then applying that learned state to generate the novel views. Window attention was applied within each image separately, bidirectionally. The state size was relatively large per block, 60 squared.
Got it. And for language modeling, that's a strict 1D sequence.
Right. For LM, the chunk size was smaller, a hyperparameter like 2K or 4K tokens. Critically, to maintain causality for text generation, they used that shifted blockwise causal apply then update order in the TTT layer. And because the TTT chunk update itself isn't strictly causal within the chunk, they needed window attention inside the chunk too. They used a sliding window attention integrated right in the same layer as TTT, sharing computations like QKV projections. They scaled this up to 32K token sequences.
Interesting, integrating window attention directly into the layer for LM. What about the video task, the auto-regressive diffusion?
For video generation, they structured the input as interleaved chunks of noisy frames being predicted and clean frames context. A chunk was typically 3 frames, around 4680 tokens. The TTT layer used a shifted, strided causal mask, updating only on the clean frame chunks but applying the state to predict both clean and noisy ones. Window attention here used non-overlapping windows covering two chunks with a blockwise causal mask inside the window, also integrated in layer with TTT sharing computations. Their largest model handled sequences up to 56K tokens, about 8.8 seconds of video.
It's clear they really tuned the chunking strategy, the update-apply logic, and the window attention role for each specific data structure. So what were the main technical takeaways from the experiments comparing SET?
The results really highlight a few key technical points. First, the hardware efficiency gains were significant. Higher GPU throughput, higher utilization, as shown in their figures and tables. This directly led to faster computation times, like processing the images for novel view synthesis was apparently much quicker compared to baseline methods.
Okay, the efficiency claim seems backed up. What else?
Second, the importance of the fast wait state size. Because LCT is efficient, they could afford larger states. And the results show that larger state sizes consistently improve performance on tasks like NVS and LM. And crucially, this benefit grew stronger as the sequence length increased, suggesting the state is really capturing that long-range context effectively. The state size itself scales with model parameters like head dimension and number of heads.
So efficiency enables larger state, and larger state improves long context performance. Makes sense. What about the optimizer choice?
That mattered too. The Muon optimizer consistently outperformed simpler ones like vanilla gradient descent or momentum for updating the fast weights, so that more sophisticated stabilization technique paid off.
And the nonlinear fast weights.
Also beneficial. The nonlinear switch ELU structure generally did better than purely linear fast weights, sometimes even when the linear model had a larger state size. It suggests the nonlinearity itself adds valuable modeling capacity to the fast weights.
Okay, and how did LCT's chunk-based recurrence compare to methods that update per token, like Mamba-style models?
That was interesting. For novel view synthesis, an image set task, their linear large chunk approach actually did better than a linear per token baseline at similar state sizes. For language modeling, a purely linear LaCT started a bit behind the per token methods. However, when they combined LaCT with a large nonlinear state and the Muon optimizer things enabled by LCT's efficiency, then it surpassed the per token baselines. So for LM, LCT's technical strength seems to be in enabling these more powerful state configurations, rather than just the chunking mechanism alone being superior to per-token updates in all cases.
That's a nuanced finding, and these technical advantages translated into better scores on the actual tasks.
Yes, the paper shows improvements in standard metrics, lower validation loss for LM and video, better PSNR for image quality and NVS, better retrieval accuracy. These results seem to tie back directly to the technical benefits of efficiency, larger state, and better optimization that LCT enables.
The results seem quite positive then. Did the paper identify any technical limitations or areas for future work?
They did mention a few things. One technical point is that the fast weight components they used don't have inherent rotation invariance, unlike some mechanisms in engine or things like rope E embeddings. They didn't fully explore the practical implications of that.
Okay, a specific geometric property. Anything else?
The range of tasks, while diverse, obviously doesn't cover everything. They didn't look at areas like, say, unposed 3D reconstruction. For language modeling, they acknowledged that computational limits restricted how far they could push model size and explore complex reasoning capabilities, which often needs huge scale. And for video generation, they noted that evaluating scalability with reliable metrics is just a generally hard problem in the field, not specific only to their method.
Understood. So limitations related to scope, computational scale for some tasks, and general evaluation challenges. All right, we've done a pretty thorough technical deep dive into LCT. We've seen its core idea of using large chunks for test time training, the interplay with window attention, the specific architectural choices around update orders and nonlinear states, and how the experiments support these technical designs across different types of data.
Exactly. And perhaps a key technical point to leave you with is that flexibility LCT seems to offer. The ability to design and optimize these fast weight systems using standard code without needing custom low-level kernels is quite powerful. As the paper suggests, this technical accessibility might make it easier for more people to work on these challenging long context problems. So maybe consider how that freedom to experiment with different state architectures and optimizers could be applied to the long sequence data challenges you might be facing.